So good afternoon. I will give you a minute to settle down and then we will get started for today's lecture. When you guys are settling down, I would like you to know that what happened last week was that it was the case that some of the lectures were a little hard to follow because there was a very unusual echo in my lecture. The echo was unusual because echo delay was I think almost like in second, which was kind of like not as disturbing as usually the echo is, but on the other hand it was also making it a little painful to follow the lecture. I checked that if there's any ways to make it more clear or more understandable, but obviously that's no longer possible to modify the voice quality. But I noticed that there's one trick that might help you, and the trick is that you can put the screen capturing on, and when the screen capturing is on, that is not affected by an echo. So you may lower the voice of my first part of my recording last week, and then then you just put the screen capturing on, and I believe that is the way to follow the last week lecture. That was the echo part. The annoying part was only like 15 minutes, a bit more than that. Rest was okay. Now what happens today is that, well, first of all, we are approaching the end of the course, so not that many subject matters to discuss anymore, but I would like to wrap up this discussion about the fatigue analysis and how a multi-body system dynamics can be used as a part of fatigue analysis. That's going to be the first topic to discuss today. And then I would like to spend some time to discuss about how is that the large deformation can be described in multi-body framework. This is going to be the main body of today's lecture. It's subject matter that is quite painful because the theory behind of the large deformation is unpleasant. It is very involving. It is mathematically quite challenging, and that's why I don't want to spend too much time to explain all possible details to you, but some of the matters that I feel that is good you to be aware of. Things that I'm assuming that is good to have, like basic engineering knowledge. Those are the things that I'm planning to explain to you today. And then the final subject matter is a master thesis. This is a soft topic, a kind of a soft topic. But I promised you that in this class I will give you a lecture about the career counseling. And then now, because of the current situation and everything, I'm not really sure if this is a good idea or not to have a lecture about the career counseling, because, you know, obviously the lecture is with no interaction with you guys. So that's why I'm not sure if I should have it or not. But what I would like to do, at least, is to tell you something that is related to master thesis topics and how to carry out the master thesis in general. That's the topic that I'm planning to discuss today. So it's going to be a coffee break already this time. So the lecture is on.
Oh, that's fine. Just
okay.
Fatten you walk a little bit.
Thank you. All right. So then, yeah. Now, again, I really would appreciate if you let me know if there's an echo problem today. And the way you can contact me is that you can use Teams perhaps, or you can send me an email. Let me just take my, let me make sure that my emails here. Okay, so you can send me an email, or you can use a Teams to connect to me. So those are the two ways to reach me today. And if I don't hear from you, then I'm expecting that there is no echo problem today. Okay, with that, let's get started and let's go through the summary of the last week lecture, and here it goes. Last week we discussed about contact modeling, and we concluded that the contact modeling itself consists of two entities, two steps, or two things to do. The first thing to do is a contact detection. Contact detection is a special discipline that is needed in order to make the contact detection to be computationally efficient enough. And that's because there is in general cases, and particularly in the game technology, number of possible contacts is very, very high. And there's no way to measure these possible contacts in every given time that the computation is carried out. But instead, something more clever has to be conducted. And then something more clever is the method that is based on the bounding boxes. In next slide we're going to take a short look about how is a bounding box is. But that's the first step. It's not the contact modeling itself, but it's the first necessary step to take. And the next step is an actual contact event description. So once the contact detection algorithms lets you know that, okay, there's a contact. The contact takes place between these two bodies in these particular locations, then it goes to next level task, and the next level task is a contact event itself. Contact event itself can be carried out by using penalty force description, which is a very often used approach, or alternatively it can be carried out by using complementary approach. And by the way, I can see that when my camera is on, I'm looking much better than last week, because the last week I did not put much of an effort to my appearance, but today even my hair is not looking as crazy it was last week. Okay, so with that, here's a little bit about how is a contact detection based on bounding box method. So as a title implies, the bounding box is a box where the bodies or systems goes inside. And now we have many different sizes of boxes and many different levels of boxes. The kind of the highest or the largest level, largest in size, is a root level, which means that the big objects are put in your world and your models in such that, you know, there could be entire vehicle or entire building that is within the one big box, and this is a root level box. And then you go more and more detailed description. Of the root level boxes, you may have a number of branch level boxes, and finally of the branch level you have a leaf level, which is a drawing primitives. And these are really the detailed description where the contact takes place. Now, this just tells you if there is a contact, and if there is a contact, where the contact takes place, between what are the bodies involved to this contact. Then you're moving on to next level, which is a description of contact itself, and typically this is carried out by using a penalty force approach. There's many different varieties in a penalty force description, but the simplest clearly is the one that we are just measuring the penetration indentation, and that's measured by, here in this equation is an x that is measured to penetration, and then we have stiffness that is associated to contact, and the stiffness it is kind of material parameter that is telling how stiff is a contact, or how stiff is the surfaces that are penetrating. Typically this penetration is power n. N here often is other number than the 1, because the 1 introduces a little bit of discontinuity in the location where the contact just takes place. If it is 2, then this contact is smooth and is more progressive, which typically helps the computing a bit. Complementary approach is completely different view to contact event itself. And this is typically used when you have a huge number of possible contacts. And this method, this complementary approach, is based on inequalities. And there's a number of inequalities, and then you're kind of using optimization procedure to figure it out how the system of very high number of bodies, how that is behaving. Remember, last week we looked at the YouTube movie from Dan Recruit, and he was calling this as a many body method, not multi-body method, but many-body method. And of course that comes from the fact that there's a huge number of bodies that are capable to contact each other. And huge number of bodies, we are speaking about perhaps million, maybe more than 1 million bodies that can contact. Again, this is based on inequalities, mathematically super painful approach, but is sometimes used in multi-body framework. Then last week we moved to completely another subject matter than the contact. So we moved to stress analysis based on multi-body system dynamics. This is needed because often information that is good to know from the virtual prototype is related to strains and stresses. And same time, even though that this is information that is often needed and is very useful information, it is not necessarily very straightforward to get that information. And that's simply because often we are dealing with rigid bodies. And even if we're dealing with the flexible bodies, where we kind of describing the deformation of particles and bodies, bodies, particles are not deforming, but the deformation of bodies, it is still not that straightforward to go from the deformation to strains and stresses. There are basically two different or alternative approaches to make that happen. The first possible approach to make it happen is that we could take all the forces that are applying in a rigid or flexible body. Because any given time solution in multi-body system dynamics, the body is in a dynamic equilibrium, meaning that all the forces that are applying in the systems are in equilibrium. That means that all the forces, external applied forces, reaction forces due to the constraints, and inertial forces, when applying all these, or when accounting all those forces, those are in dynamic equilibrium in any given time. So we can take those forces and we can use it as an input field in our finite element model. So meaning that the forces from the multi-body system dynamics are used as forces in finite element modeling. Now using the finite element modeling, it is possible to describe displacement, and from displacement you know that the finite element software very easily can compute the strains and stresses. So that's business as usual. So this is that option number one. So we taking the forces from multi-body system dynamics and use them in finite element software. Not a very straightforward approach. This comes with the number of practical difficulties, including the fact that even though the body have to be in, or the body is in dynamic equilibrium, and in theory the body should not move anywhere if you impose all the forces on it. But in practice, you have to be able to take a rigid body motion off in your finite element modeling, and that have to be carried out with help of boundary conditions. And the boundary condition could be not easy to select in general case, and this is something that often is quite a bit of headache to carry it out. Now this method, even though that is very simple and very coarse method, has a very fancy name, and so meaning I'm speaking about again this method, and the fancy name is called linear theory of elastodynamics. Sounds very sophisticated, but when you look at what's inside of there, it's not so sophisticated. Then an alternative approach, and the alternative approach is that we will actually take a full advantage of the fact that flexible body is described by using modal reduction technique, and using particularly the fact that information needed in modal reduction is coming from the finite element software. So in addition to this modal information and the description of deformation, we can also export the information that relates displacement and strain and strains and stresses. And that's just a little better software technology that makes it happen. And now it's possible to plot out the stresses directly from multi-body software. No need to recompute the deformation, or no need to recompute the forces. It will be way more straightforward than approach number one. Okay, finally, now what we discussed last week. Shortly, by the way, that the first in-class quiz will be in this subject matter. We discussed a little bit about the fatigue of welded structures. And welded structures are very special structures, and that's because of the two different things. First of all, welded structures can be assumed to include initial cracks. So the cracks initialization process that is very lengthy in terms of non-welded structures is non-existing in welded structures, because the welding process itself introduces very microscopic, very small microscopic cracks to welded toy. And welded toy is the one that is located right here. So if you see my pointer, and yes, you're able to see that. So that's where the welded toy is located at. So when you look at that very, very carefully, there is a microscopic initial cracks. So even though that you have a brand new vehicle or brand new bicycle, it is still, if it is made by using a welding, it is a fair assumption to say that there are initial cracks. And then it's all about the crack propagation process. That's what we have to be able to control in welded structures. To make sure that, they understand that there's a crack, but make sure that the crack is not growing too much. And now, crack propagation is the one that takes most of the time in fatigue life of welded structure. And the other problem, so I was sorry that I got a little bit misled. So first problem associated with welded structure is this initial crack. So it's there. It's very difficult to get rid of that. Then another problem is the fact that, again, due to the welding process itself, which is kind of violent process, there's going to be a very high amount of residual stresses. Again, very locally, roughly the same area that initial crack is located at. There are very high residual stresses, and they're typically roughly in a position where the linear strain displacement relationship is turned out to be non-linear. The plastic deformation. And that's a problem, because as soon as we start loading the structure, we're moving from linear to non-linear phase. And you know what that means? It means that there's a permanent deformation. Not in a way that you can visually see that something is bending or distorting, but the crack is growing in the structure. And that's a mechanism that is a problem. Another problem in a welded structure. So, summary, the welded structures are suffering because of there's an initial crack and there's a high residual stresses. So how are the ways that we can then improve the fatigue life of welded structures? Well, if we're going to select the high or ultra high strength steel, it's not going to help us. And it's not going to help because, if we're dealing with the high or ultra high strength steel, this linear curve will be just longer. Now the residual stresses are not really care about that. So even if you have a high strength steel, you have much longer linear phase, let's say that it ends roughly here, residual stresses will be again, in a corner when linear turns out to be non-linear. So no help whatsoever. Only way that you can really help it is that you have to get rid of this initial crack. An initial crack you can get rid of by using post-weld treatment techniques. And those are like hammering this particular location, this toy, or using TIG welding perhaps. There are a few techniques that helps you to get rid of this initial crack. So soon there will be in-class quiz, and some of you, I can see that you're already logged into Socrates, and there's a question where I'm asking how, the question is, fatigue of welded structures can be improved by, and then there is several choices. Now, we can get back to that in a second, but let's just complete this story about the fatigue analysis. And sorry that I'm a little slow today. I'm getting started with the new subject matters. Now, fatigue analysis itself, and now we're speaking about not what happens in reality, but how is that we can use a computer technology to make a prediction about fatigue life. You know, what is needed in a fatigue life prediction is that we have to get the stress history one way or another. And now the stress history is something that it could be, let's say, how are the stresses within the one, say, an hour during the operation of machine, or how are the stresses within the one work cycle, and so on and so forth. It doesn't really matter what's the scale, but this will be the scale how the fatigue will be then measured. Let's say that, you know, here I have a hypothetical work cycle, and the hypothetical work cycle is like using the crane. It could be that lock crane that is taking a hold of a lock, lifting it up, and now this is where the crane is with no loading. Here's when it is touching the lock, and then is moving the lock to one location to another location. And now during this movement there is some fluctuation of stresses. And now what I have here, just make sure that you understand what I have in this picture. I have here time versus stress. Now this again is the location that I'm touching the lock, I'm lifting the lock, and because of the lifting the stress will be going up. And now due to the motion, due to the dynamics, it's fluctuating a little bit. And then I will place that another location and release the lock, and there's a little bit of fluctuation again. What we need to know in the stress history, or from the stress history, is we need to know what are the stress deltas, what are the kind of the loops that are closed in this history. And the loops are like you loading and unloading. These are the kind of like deltas that takes place, and we have to measure all the deltas. This hypothetical work cycle consists of several deltas. You know, the first one is that you lift the lock. So you started here, you're coming back here. So that's one delta. Then these small deltas as well are introducing, this small fluctuation as well are introducing small deltas. Each of them can be dangerous. Some of them may be lower than the threshold value that is not allowing the crack to crawl, but generally speaking, all of them can be something that is good to take into account. Now, the way to figure out these deltas can be carried out by using a method that is called rainflow analysis. Rainflow analysis is a method that you kind of assuming the stress history to be a shape of a container. Let's say that I have a container. This is a little bit of a funny thing, but let's think that gravity is pointing upwards. So I have a container that is this funny shaped container. Now what I will do for this container is that I will allow this container to have as much water inside as possible. Okay, so it's meaning that there is there's been a water level. One water level will be here, another water level will be here, another one will be here, and one more will be here. And then you just start opening valves from these peak values and try to get the water off from your container. Now let's say that I'm opening the valve here, I make it drilling to this particular location of my container. Water level will go down all the way from here to here. So this is your first delta. But obviously water will stay here, so you need to make some more drillings. So this is where those small deltas are coming from. So when you're drilling this one here, then the water level will come from here to here, but what is left is this one here. Again, you're drilling here, you get third deltas. Here the same way you're making drilling. This is the way you figure out what are the deltas. And that's why it is called rainflow analysis. Now, once it is clear what are all the deltas in the system, then you can use a very simple equation to estimate what is an equivalent stress loading. Equivalent stress loading means that all these large and small deltas will be replaced by one delta only, which is equivalent in the damage wise than the full work cycle. So all the small and large deltas will be replaced by just one delta. That's the information that you will then use to make an estimation about stresses. Now, this is what happens in reality. In reality, this is what we shortly look at. In reality, when you look at what happens very close to location where the crack is growing, there's a lot of geometrical nonlinearities. And these geometrical nonlinearities will increase the stress applying right when the crack is growing. Using the multi-body system dynamics, these rays of stress due to the local geometrical non-smoothness cannot be accounted. We cannot really take those into account. So only the level of stresses that keeps the entire structure in equilibrium, that's something that we can take into account. But not the local stresses due to the geometrical nonlinearities, that we cannot take into account. But if you want to use these stresses in order to make a fatigue prediction, then you can use literature or make a very detailed finite element models to try to see how these local geometrical details are affecting to your results. Okay, so simulation. You can get the nominal level stresses. So again, so I'm speaking about this level of stresses that are not affected due to the geometrical non-idealities. And this is where you can do the fatigue life estimation. We are not going to take a look at the details, but that's how it goes. If you want to move on to more detailed description, then you can use parameters that are coming from either literature, detailed finite element, boundary element analysis, measurements perhaps as well. And even if you want to use a fraction mechanics, again, you can use a literature or maybe detailed finite element boundary element analysis. So typically in the multi-body dynamics, we are limited to this particular section only. Alright, so here's an example. So here is a crane that is hydraulically actuated, and these consist of 3 hydraulic circuits, 4 flexible bodies, and the bodies are the pillars here, lift arm, swing arm, and then the telescope arm that is now active in this figure. Now the hydraulic circuits are lift arm, swing arm, and then the rotary actuator that is the one that is turning the crane. And the crane is loaded by a mass. The mass is this one here, and the mass is connected to end of the crane by a rigid link. This is how, I need to apologize that the quality is blurred, so it's not very good quality picture. But now if you take a really close look at this particular person here, it's too bad that you are not with me in the lecture, because it would be so much fun to organize a competition to guess who is this. Yes, it is me. Sad to say that I'm unwilling to do the math, but yes, 25 years ago, more or less exactly 25 years ago. So this measurement was carried out as part of my doctoral dissertation. Now, then this is how the stress history looked like. So there's a measured and simulated stresses, and the stresses are coming from using this linear theory of elastodynamics technique, and the measurements are carried out by using strain gauge. Now, like you see, the match is very good, so it's looking very good. And we were looking 2 details here to estimate the fatigue of these details. And the particular problematic detail was the one that was located here. Now, by the way, this crane is still located in the university laboratory. Now the laboratory is run by Heikki Handros. But anyways, so one of the lessons that is important from this particular structure is that you have to consider welding as a kind of like a good friend that can be your enemy as well. Good friend that can be your enemy means that you have to be able to understand that the welding is a risky business. And that's again because of these 2 mechanisms, because of the initial crack and high residual stresses. So you don't want to put the welding into location that is highly loaded. And now here's an example about this particular crane where most of the welding are really nicely made. They are not located in the areas that are highly loaded, with an exception, and the exception is this one here. You know, there's a welded knot, and the knot is just used in order to make hydraulic pipes to travel from here to the swing arm. So these dots or these knots can be located anywhere you want. And because they can be located anywhere you want, it makes no sense to place them in a highly loaded area, because again, they are welded to main boom, and because they are welded, you know, there is an initial crack, there's a high residual stresses, and this is where this particular crane was actually damaged. So lesson is that make sure that you're careful with where you're placing your welds. Okay, now I go back to this question that I mentioned earlier. A fatigue of a welded structure can be improved by using a high or ultra high strength steel, using paintings or other finishing technique, which makes kind of sense because, you know, if there's a crack, you paint it, you don't see the crack. So it's like if you don't see it, you don't have it kind of technique. That's an option number 2. And then the option number 3 is use post-welding treatment techniques. And those are hammering or other techniques that you want to get rid of the initial crack that is located in the welded joint. So now, stroke adhesive is open. So go ahead and log in. So I will take a look. How is your performance today? So we have today 12 students. 10 already answered. Just one more is missing. Oh, we got more students. Okay, so we're done. So here it is. Okay, so what is your estimation? What do you say? I think because, you know, now there's so strong hints what is a correct answer, that I think this is going to be not 100%, but 90%. 90%. Okay, so really good. So really good. So using high or ultra high strength steel is a little bit problematic because it's not really solving the two problems associated to welded structures, but using the post-welding treatment techniques, this is the way to go. And why this is not solving? Because residual stresses and initial crack. Okay, now what follows is this discussion about large deformation. Now I really would need to get your feedback, you know, whether or not you want to have these career counseling. So if you felt that you would like to have a career counseling, I'm willing to do that next week. So next week lecture anyways will be just kind of wrapping up everything so far. I mean, wrapping up all the matters from the second period. So I'm planning to to summarize all these visiting lectures. I'm planning to give you questions that are perhaps asked in exam, and then if you want, that's an opportunity that we can discuss about career counseling. Now, there's going to be some practical information available on next Monday. So next Monday I need to explain you how is it the exam will be carried out, what are the details related to exam, when the exam will be, so on and so forth. Already this time that it's clear that there is no, I mean, for me at least it's clear that there is no classical exam, so there will not be a paper exam in a way that usually the exams are organized, or the way that you participate the first midterm exam. That's not going to happen. But instead, and it's not going to happen because some of you are already back home, so I'm back home meaning not in Finland any longer. So I will organize the exam using the modal, And this time it's not going to be the same way like in a simulation of a mechatronic machine, that there was a question bank and I'm making a lottery from the question bank, but instead I'm just give you a certain time that the exam will be open. It's much more limited than usually. It's just one day, maybe 2 hours or so, 3 hours max, and then you will have one attempt to do your exam. But these are all the details that I need to get back next Monday. Now, what's deformation? I'm going to explain a little bit about method that is used usually to describe large deformation. And this is because a few years back, all the teachers, all the professors got the message from student union, and in the message it became clear that students would like to learn more about the subject matters that are under the research in LUT. Now here's a topic that is under the research in LUT. So this is a method that is particularly designed to capture large deformation in multi-body applications. And that's what I'm about to explain to you. You know, I'm not going to go in very much in detail, but there was a little bit of mathematics involved. But I will keep it in a level that is still more or less enjoyable for you. Now, let's get started from the background. So why is that we do this? And this was actually a slide that I showed you already last fall in the course of simulation of a mechatronic machine. What is that we have in this slide is that this tells you a little bit about trend and big picture in the multi-body system dynamics. You know, the multi-body system dynamics all started in the case of rigid bodies. So it's a method that is designed to deal with the rigid bodies. And soon it became clear that in order to make more accurate predictions about dynamic performance of different machines and systems, it is necessary to capture the mechanical deformation. And mechanical deformation often is not very large, but is moderate, like in the case of connection rod and crankshaft. This is where you can model by using floating frame reference formulation that we are all familiar with. Now in some cases, even the floating frame reference formulation is not enough, but you have to use more heavy tools than that. And that's where the absolute nodal formulation comes into play. And that's the method that is designed to capture very large deformation. An example is a belt structure shown in this picture here. So the belt here undergoing very large deformation, and to capture that particular component you cannot use a floating frame reference formulation, but you have to use a method such like the absolute nodal formulation. So now we're going to take a look at the kind of like a big picture of the absolute nodal formulation, and then let's see how much it takes. And if we have enough time, then I'm going to discuss about master thesis topics. Now, what is an important thing when selecting master thesis? Now, the absolute nodal formulation, that's the method that we're going to discuss, and that's a method that fits well to structural elements. And structural elements are, roughly speaking, cables, beams, plates, cells. Kind of that we are calling the special structural feature. And the structural feature, like in a beam-like structures, is the fact that beam is very long and the cross section is very small when comparing the length of the structure. Plates and cells, they are very thin, and that's a special feature related to that. Cables is a kind of like a special case of beams, and this is where the absolute nodal formulation fits well. So it's not using solid elements. You know, the solid elements is something that you can model pretty much everything you want, but it easily gives you very high number of nodal degrees of freedom. Whereas using cable, beam and plate elements, you typically don't need that many degrees of freedom. Now, the special feature about absolute nodal coordinate formulation, this is really the core feature of the method, is that it can describe kinematics from any kind of configuration by just using the element shape function matrix and the vector of nodal degrees of freedom. This is already that tells that this is very different than conventional finite element method, because this is used to describe kinematics in conventional finite element method as well. But kinematics as shown here in conventional finite element method cannot describe large rotations. This one here can describe large rotation. How this is possible? Well, it's possible because the method is treating slopes a little bit a special way. Slopes are partial differentiations. Here's I know that things are coming quite fast. I'm not expecting you to have a full understanding about all the details, but if you understand the big picture, that's already awesome. Now, going back here, in conventional finite element method, this can describe deformation, but not large rotation. In absolute nodal coordinate formulation, it can describe deformation and large rotation. And why is this possible? That's because there's some clear difference between conventional finite element method and the absolute nodal coordinate formulation. Now here's the beam element. This is a kind of the beam element we looked at previously in this course. And in this beam element, I have a total of 4 degrees of freedom. And these degrees of freedom are displacement in y direction in node number 1 and node number 2. And then the slopes, which is a partial differentiation of y partial x in nodal locations. So that gives you 1, 2, 3, 4 degrees of freedom. So 4 nodal coordinates. Shape functions, well, those you can carry it out by using polynomial expansions like we discussed a couple of weeks back, a couple of months back actually. So how is this then different when you're using the absolute nodal coordinate formulation? Now, instead of using displacement in one direction, displacement in nodal location is described by using a vector. A vector R is here in the planar case is consisting of 2 components that are displacement in x and y direction, and then the slopes with respect to length of the element. So the slope here consists of 2 components. Position consists of 2 components, slopes consist of 2 components. So each one of the nodal location there is a total of 4 components. So even in this simple planar element, I have here 4 nodal degrees of freedom located in this node, another 4 here, so there is a total of 8 degrees of freedom. And because of this additional nodal degrees of freedom, it is possible to capture the large translations. And that's the special feature of absolute nodal coordinate formulation. Now if you understand that, that's awesome. I'm not expecting you to understand any further than that. But except that if you still this is like a common engineering sense. Common engineering sense is related to transverse shear deformation. Transverse shear deformation is something that is needed if you're dealing with thick structures. In the thick structures, the transverse shear deformation makes the structure to behave in a little bit of unique way. Conventional finite element method or in conventional finite element formulation, shear deformation is captured by using rotational parameter. A rotational parameter in a conventional finite element method is not equal than the slope, because when there is a shear deformation, the cross-section orientation is not necessarily perpendicular with respect to midline. Actually, that's exactly where the transverse shear deformation is coming from. So it's this kind of like not making the cross-section to behave with respect to midline in a way that slopes predict that to happen. And that's can be accounted by using this rotational parameter, but in absolute nodal coordinate formulation it is captured by using more slopes. Now this is becoming already quite much, because now in one nodal location here I have R, that is describing where the node is located at, and then I have here one slope vector in the longitudinal direction, another one in the transverse direction. So that's a 6 degrees of freedom located in a one nodal location. Here's another 6 degrees of freedom. So this simple element, planar beam element, already consists of 12 degrees of freedom. 6 here, 6 here, and that's what makes already this very unique. Now, in a case of plate elements, we can use the same procedure. We can just extend that in another direction. So we can again play with these slopes. And now the important question is that, if going back here, now 6 degrees of freedom per nodal location. So how come? Because in planar case, what I can understand is that there are true translation. Translation in X, translation in Y direction. I understand that there's a rotation, but what are the rest? What are the rest degrees of freedom? Because there is still 3 left. So what is a physical interpretation of this additional degrees of freedom? Because they have to have a deformation of some kind, otherwise they don't have a stiffness. So what is it they have? So this is how it looks in a beam structure, but this question that I was about to explain, what these additional degrees of freedom, what is that they describe? Well, they describe cross-section deformation. And the cross-section deformation, or fiber deformation in the case of plate, so this is a plate structure. Cross-section deformation means that the cross-section can distort, like shown here. It can be longer and it can be stretched, it can be compressed. So this is how it behaves. So cross-section deformation that is typically never ever accounted in conventional finite element method is now accounted in the absolute nodal coordinate formulation. So that's a special feature. So now I know that this is, I don't see your faces, but I'm kind of guessing that this is, well, this is as painful it gets. But let me go back and let me try to explain what are the kind of the thing that you need to know in terms of written exam. So let me go back here. Okay, the absolute nodal coordinate formulation. This is a method that the kinematics is super simple, because the kinematics of deformation and large translation and rotation, rigid body translation and rotation, are all accounted by using a simple linear combination of shape function matrix and vector and nodal degrees of freedom. Conventional finite element method is not behaving like that. It is not capable to describe these large rotations and large translation using this simple kinematics. So this is the first thing that I'm expecting you to know. The second thing, how is this possible? It is possible because I'm adding nodal degrees of freedom to one nodal location. So in one nodal location I can have many degrees of freedom. Some of them are related to physical displacement orientation, but some of them are related to what happens internally, like what happens to cross-section itself. And that's what the absolute nodal coordinate formulation is doing for you. And the cross-section, the transverse set deformation, which is important in case of thick structures. Now this is what you need to listen. Transverse set deformation is important in case of thick structures, because I'm going to ask that in a second in my class quizzes. That can be captured by using more slopes in the absolute nodal coordinate formulation. So more and more slopes. And what is a consequence of these more and more slopes? I'm describing more and more cross-section deformation. Clear? I guess it is quite clear. Okay, then how is that you can compute the elastic forces? I'm not going to take a look at that in details. I'm just saying that It can be based on a continuum mechanics approach, which you guys, I don't think you have much of a knowledge in that particular field yet. You might have it in a bit later, but not yet. But it's very straightforward. It's not needed any particular skills, because strains can be computed by taking a partial differentiation of this r with respect to x, and this is what you can get automatically from the nodal degrees of freedom. And this allows you to give an estimation about the strains, and using the matrix of elastic coefficients you can get elastic forces. So it's super straightforward, just these two equations and that's it. Now this, what I will do is that I will ask this first, and then I will go to a little bit of further explanation about the features of the absolute nodal coordinate formulation. So here's a question related to transverse Z deformation. So when it is important to take that into account, and I have here 4 choices. In case of large deformation, in case of thick structure, so if I have really thick structure that I have to study, or in case of thin structures. Never is my final option. So let me move on to my in-class quizzes. So it's open, so take a look. I'm gonna have a coffee while you're entering your answer. Okay, so it's happening really fast, so I can see that it's just the one student that is still thinking, but I'm not sure if this, because last time it was 13 students and 13 answers. Now I got 14 students, so let me see if I got one more answer. So here it is. This is a difficult question, so if you haven't followed my streaming, there is no way to answer this correctly, because if this comes out of the blue sky, it's super difficult. So the one student was missing last time, so let me take a look. Oh, very nice. 85%. That's now there was the final one, which was incorrect. So large deformation not related to this subject matter, but it's a thick structure that it is needed. Thick structure, then you have to use an element that is capable to capture transverse Z deformation. Okay, now just shortly. This was a long time ago, 2003, a really long time ago. There was a very important discovery about the method, and the discovery was the fact that, I'm speaking about the absolute nodal coordinate formulation. The discovery was the fact that this method too is suffering from different lockings. Locking is a very common problem in finite element method. What it means is that sometimes element is unable to predict correct answers, or it's converting super slowly, meaning that even in a case of simple cantilever beam like this one here, the converging takes hundreds of thousands of elements to get the correct solution. And of course this is not how it's supposed to be, because simple example like a cantilever beam, you should be able to get the correct prediction by using 1 element, 2 element max. But if you have this locking, then you may not be able to do so. And this is very common in the finite element community, that elements are suffering from different kind of locking mechanisms. And the usual remedy, usual way to fix lockings in finite element community is that you are using, well, typical way is that you're using lower order integration. So you have problem in your kinematics and you're solving the kinematics by doing the integration incorrectly. So if you're not familiar with the finite element technology, it's going to be very hard to understand that. But generally speaking, there is a problem in a kinematic which you're fixing by making another mistakes in your computing. But the beauty of these two mistakes is that they're compensating each other, and you eventually get the correct solution. So that's a typical way to fix mix the locking mechanisms. The same particular way is used in absolute nodal coordinate formulation as well. Now there's many different kind of elements introduced in the absolute nodal coordinate formulation. There's possibility to increase or decrease the number of slopes, and with that you can put it you can make it suitable for many different applications. So here are just a few examples what are the practical applications. So well this is not the practical application. The first one, this is a flying spaghetti. This is just telling you how is a very flexible body behaving when you are introducing the moment, like shown here at one end of the beam-like structure. Why this is actually used is that this is a good reference solution that you can use in order to estimate the accuracy and computational efficiency of new methods. So that's why this was also studied by using the absolute nodal coordinate formulation. Okay, so here are the more practical cases. So it can be used in the belts, like we discussed in the very beginning, cables like this one here, and it can deal with the large deformation. So here, this is where it comes really handy, and it being applied to cables, and in the cables it being used in a very interesting way. So it's being used by using this method, which is a arbitrary Lagrangian Eulerian approach. This is very interesting because arbitrary Lagrangian Eulerian approach is a method that allows you to change the length of an element during your simulation. So it means that, or it's actually very handy in the case of, say, cables or hosting machines or lifting machines, where typically the cable is coming kind of inside of the machine and then it's becoming longer when you are touching something, and when you're lifting it up the cable comes shorter. And typically this is computationally super intensive computing, because in order to compute the structure here, the element length is limited due to the radius of the pulley here, because the cable or the element of the cable have to be able to go over this particular structure. And there is no way that you can model this by using one or two elements, but instead you have to use many elements. Now, because of this, here too, element length should be constant all the time, because it's possible that any particular cable part comes into contact with the pulley, and that's what limits conventional approach. Now this new approach, this arbitrary Lagrangian Eulerian approach, is very clever because it allows you to change up the length of element. So here you have all these four elements that is always applied to this pulley location, and the element that is in this free span here can change its length. And this is super nice, because then you can use optimal amount of elements for cable problems. And this is again method based on arbitrary Lagrangian Eulerian approach. Okay, here are some other applications. It can be used in railway application or railroad applications, modeling of tires, leaf springs, and so on. In biomechanics. Biomechanics, by the way, is a really good application to absolute nodal coordinate formulation, and that's simply because in the biomechanics there's a lot of soft tissues, and these soft tissues are experiencing large deformations, really large deformations, and that's where the absolute nodal coordinate formulation is very handy. Here are some very special applications where there's electromechanical couplings, fluid mechanical couplings, optimizations, and then the last trend that is related to this absolute nodal coordinate formulation is this NURBS business that I shortly mentioned to you. Now, this is the subject matter that I will have my next in-class quizzes. So now you need to take your coffee away and you need to put the full attention to me, because what I will about to explain I will ask after 2 slides. Now, this NURBS, which is a non-uniform rational B-splines, this is the description that is used in a CAD software to make graphical representation of, drawings subject. Like SolidWorks, they're using NURBS because in a NURBS you can make any kind of graphical representation. So basically, in gradients there are NURBS based. Now, the big problem in the finite element modeling is that these NURBS have to be converted to be polynomials in a big picture, because you need to take your CAD drawing, maybe reduce a number of details there, and then move that to your finite element code and mesh it. And that means that you take your NURBS representation, original NURBS presentation, and converted that to be representation of polynomials. And that's meshing, but that's essentially meshing. Now, if there's a clear relation between the graphical representation and representation how the elements are described, that often helps. And now this NURBS is something that which is again non-uniform rational B-splines, is something that absolute nodal coordinate formulation is directly related to. And that helps to do the meshing process itself. So meshing is very straightforward to do. Usually it's very painful. Now, because it's so painful, there's a little bit of new trend in the finite element community. And the new trend in the finite element community is that instead of using polynomials, they would like to use NURBS as a kind of like the structure, how the elements are derived. Remember, we used the polynomials in the very beginning, and we use this Pascal's triangle to select the polynomial coefficients. Now we could forget about polynomials and use directly NURBS, non-uniform rational B-splines, to give an estimation about how the particles are expecting to move between the nodal location. And now if you're using these NURBS to describe how the particles are expecting to move within the nodal location, then the meshing process will be very straightforward. And now if you decided to use these NURBS, then you are discussing about the method that is called isogeometrical analysis, because it is geometrically so well mapped to geometries that I use in the CAD software. That's what I'm about to ask. What is an isogeometric analysis, and what are the components used in isogeometric analysis? So keep that in your mind, because soon I will be revisiting in that particular topic. Now, prior to that, here's a summary of finite element the absolute nodal coordinate formulation. So in absolute nodal coordinate formulation, we're using slope vectors to describe the orientation, not rotation, but the slope vectors. And we can describe the kinematics by using this symbol notation. And because this is a linear relation, it applies also in acceleration, like shown here. Equation of motion is super simple. Now, it can be applied to a number of practical applications, such like vehicle dynamics, biomechanics, rotating structures, optimization, multi-physics analysis, cable dynamics, and so on. So here's my answer, my question, in-class question. In isogeometric analysis, finite elements are based on NURBS, finite elements are based on polynomials, finite elements are based on trigonometric functions, finite elements are based on imaginary functions. Now when I'm saying based on, Like what is that we will get started on. Okay, so let me... Okay, so it's on. So you can go ahead and enter your answer. And then while you're doing that, gonna just see what are this okay, I have 11 answers already. Master thesis. Now if you already made your master thesis or you're not interested in this subject matter, that will be alright to leave this today's lecture. I'm planning to spend some 20 minutes or something explaining what is something that is good to take into account when searching a master thesis topic. Okay, I got 15 answers. I have all the answers already. Okay, this is difficult. I don't expect that success rate to be super high. I'm saying 75. What a surprise. Big surprise. Very pleasant surprise. So that's a good score. That's a really nice. Now look at that. 93. That's in this difficult question. That's good. Okay, now I'm gonna put this aside. Now those of you that are not interested about the master thesis, I wish you, hold on. I wish you a good day, and I hope to see you on Monday. Those of you that would like to learn a little bit about the master thesis, please stay with me another 20 minutes or so, maybe even less than that. Okay, so here's my instructions to you regarding the master thesis. So the four things that I would like to discuss is beginning, like a little bit about the background, a little bit about how is the nature of the work, then my instructions to you to carry out the work, and something about the reporting. Now let's get started from the beginning, and the beginning is of course topic selection. So where to get to topic, and here's a possible ways to get to topic. So you can get it from a professor. You can be active by yourself by contacting companies. I know we are experiencing very special and very unique time, and the companies may be confused what will happen next, and they will be very hesitated to hire new people. But I'm sure this is not going to take too long time, and within a reasonable time range we are back in a normal mode. And back in a normal mode meaning that there are a number of companies that are offering topics, master thesis topics. And how is that you can find it out? Is that you can maybe use your own contacts if you have any. And if you don't, then you can contact companies by searching the opportunities using this particular website. This particular website, let me show how it looks. This is student handbook, and let me show how it is to you. So it's loading. So this is how it reads. So let me switch this to English. It's a little slow. So here is quite a bit of instructions, different steps, where to look for jobs, interviews, salaries, contracts, so even information about that. But let me see, what are them? Careers, toolkits. Let me see, I haven't been here for a while. But this is something that definitely makes sense to look at. This is that book that I mentioned. 2020. So this is a very recent book. I think this is written in Finnish. I think so. No, this is in English. No, in Finnish. I'm sorry about that. But this tells a little bit about, oh no, there are English as well. CVs, how to contact the companies and so on and so forth. And what are the companies and where are the company website. This is really good tool set for you. Now, what are the benefits if you're contacting the professor? We're going to take a look at it in a second, but it makes sense to contact your supervisors anyways, because you know, even if you get the topic from the industry, you still need to make sure that it is suitable as a master thesis topic, and that you can get the confirmation only from your supervisor, not from your fellow student. And because you have to be in touch with your supervisors anyways, it makes sense to do it as early as possible, even in a time that you're kind of looking for different opportunities. Contact your supervisor very early, because your supervisor may have a topic for you ready for you, which in this time, really don't know if that's the case or not, and can help you to keep your contacts to companies. So maybe there's a list of topics available, people, you know, or kind of like contacts that the supervisor have, and helps you to get the let me see what. Okay, so like maybe there is a companies that he knows or she knows that are looking for candidates this particular time, so that's why it makes sense to do it. And this topic matter is as well as important. And then of course, you know, prior to meeting your supervisor, it's good to know that what is a kind of areas that you're interested in, what are your strengths and weaknesses, a little bit about the career counseling. These are the good things about the salary. I mean, industry versus university. In industry, it's quite often the fact that you get the salary some kind. Not if not salary, then you may get scholarship from the support foundation. I will explain that in a second how it goes. And the big benefits in industry is that typically the thesis positions are used to kind of like a test period for individuals to see how is they performing. So usually there is a permanent position waiting for, and if you are doing well in your thesis work, then they will hire you as a permanent employee, and that's of course is a really beautiful thing. What a good thing about the university is that you can get the support from a professor, location. I mean, in a way that if living the usual life, you could be able to participate the courses, exams, and so on in the university premises. But of course, you know that that's not the case today. Now, a little bit about the topic selection. You know, it's good to define the commitment of your supervisor company. Sometimes the company commitment is really, really important to learn. All responsibilities that is associated to work. You know, salaries, project that is related to this dissertation work, how is it you can make yourself stronger, because end of the day, thesis is still, you know, part of your studies. This is very important to keep in mind. It is still part of your studies, and it is designed to make you stronger and make you more independent. So you need to consider, is this particular topic is actually doing that for you or not. And then also sometimes it makes sense to figure it out if you are strong enough to do that particular subject matter. So if you have all the knowledge that is needed in order to carry out that particular thesis topic. And then it's important to know that now this is a little bit of once in a lifetime opportunity. So you cannot start your work and then close it and started a new topic and close it and started a new topic. That's not going to be acceptance. It's not going to be accepted in a department. It's not going to be very good for you. It's going to be very bad for you if you're in a situation that you have to cancel your work. So you have to consider this as a topic is selected just once. And also that is important is that topic itself is not defining your grade. It's not that the professor is giving you the topic then you will automatically score 5 out of 5. Or you will get very practical work from industry and you will score 3 out of 5. It's not like that. The topic is not defining your final grade. A little bit about salaries. Is typical way to get the financial compensation is that you get the scholarship from the support foundation, and information about the support foundation can be found here. So let me show how this website reads. So it was this one here. So this is LUT support foundation, and how it goes is that once you find a topic from industry, then company can design it to give you financial support with help of support foundation. So it's meaning that they will make a donation to support foundation, and then support foundation in turn give you the scholarship for that particular subject matter. And money wise, because the scholarship is tax free, this is roughly equal than the salary, of course depending on how long you need to spend to do your thesis work. But roughly this is more or less same money wise. You can get the salary from the company. There was cases that you can get the salary from university or no salary, which I think it is a right option too, because remember, end of the day, this is part of your studies. So the idea is to make you a stronger individual. So you're the one that will benefit the most. Even, I'm not saying that, the salary is nice to get, but there is a bigger picture than that. And that's the fact that you will get your degree and you will be much stronger individual. You will be much stronger in the work market as well. Okay, nature of the work, just a few notes related to that. So thesis is 6 months. It's an independent work, so you cannot do it with your friend. You have to do it by yourself. And the idea is to demonstrate that you are mature enough to carry out the work, and you can kind of put the pieces together in a subject matter that you are not having prior knowledge, or you don't have a strong prior knowledge. And well, in other words, it means that you have to demonstrate your ability to solve large problems. How it goes then? It goes such that there is 6 months in the length, and typically there is a 1 to 2 months, and then there's a kind of like a checking like how things are progressing, and then there is a 1 to 2 month checking how things are progressing, final evaluation. So these screen bars are a communication with your supervisor, and it could be email communication, it could be Skype meetings, it could be face-to-face meetings, it could be many different varieties. Here's my instructions how to carry out the work. Now, my instruction is that it makes sense to make a table of content in the very beginning, kind of creating the plot, storyline for your thesis. Because, the storyline, the plot, it first of all helps you to focus. So it helps you to make sure what are the subject matters that are not core content of your thesis. Also, it can be used as a timetable, in a sense that, if you have, different chapters that will be in your thesis, and you realize that you've been in the introduction already 6 months, that you're in a serious problem. So table of content is something that is super important. It's important to organize a kickoff meeting with your supervisor and whoever is a company or whoever is the benefiter of your work, and then make a high quality literature review in the very beginning, because it's possible that something that is very closely related to your thesis, you find it out in a too late phase, and that's very unfortunate. So all the important literature is good to figure it out as soon as possible. And the good literature review you can do by using Google Scholar, Scopus, Web of Knowledge. Each of them are having some advantages and drawbacks, and it makes sense to use all of them. And really the writing is something that is very heavily recommended to do in the beginning. because if you don't do the writing, then it's going to be super painful to do that in the very end of the thesis work. And keep in mind that this is just the one course or project. This is not going to make the work go around in a different direction, but it's your way to put yourself in another level, not more than that. You know, these are the people that are involved with, so they're student, supervisors from university, instructors, maybe one or two from the company university. So it's a team, still a little bit of teamwork. So you're not by yourself, particularly if you decided to use the help of others. Now, finally, a few words about the reporting. I'm not going to spend here too much time, but strictly speaking, generally speaking, perhaps better say, you know, the thesis should follow this inbred structure, you know, the structure that the thesis consists of 5 chapters. And it's quite surprising that this instructions fits to many different subject matters, even though that initially it may sound that how is that my work can be put in this framework. But yes, it's typically possible to do that. And now, something that is important is that you have to write an introduction in a way that you're kind of introducing the subject matter to readers. You're explaining what is an objective of your work. You're explaining what is the reason you do the work, and then you have to check, once you jump to conclusion, if you're still speaking about the same subject matter. It's possible, it should be possible to read the thesis such that one is just reading the introduction, you know, what is the subject matter, what's the most important literature, what's an objective, and then skip this, and check from the conclusion what was the most important observations. Were you able to reach the objectives? What happened in a way? So it should be readable like that. Here's a little bit of, you know, my instructions, what should be in the different chapters. You know, purpose and objective of the study, that's clearly super important point in introduction. My recommendation is to use a figure or something to illustrate what is the subject matter. You know, references, references, standards, previous studies, application is good to mention in the introduction. Then the method section really depends on what is the subject matter. This is too much about the simulation. It doesn't need to be that area. The results is that you are explaining what was the outcome of your work. And then in the discussion, you're looking in an objective manner, you know, how it really feels, what are the benefits that you can create with your, how is the results, what are the observations you can make from the results. And then conclusion is just a summary of the work. Well, here's some general instructions. You may follow these. So figures must be always referred in the text. Explain it like you explain things to me. You know, something that takes some time to learn it. So don't expect too much from your reader. Make sure that the headings are corresponding to the content. And here's some other instructions. Use passive voice. Don't try to be funny. Oh, this is important because every now and then there is a student that want to make jokes in the thesis work. There is no single cases that we've been laughing, so it's never ever a funny thing. So this is not the comedy book. Instead, try to be boring and try to use exact engineering language. While saying that, still you need to avoid uncompromised language, like saying all machines are this and that, because there is an always exception. And because the exception, this uncompromised language is not a good policy. Unspecific statement, quite large. This kind of statement is not very clear, so it's very unspecific language. Don't mix languages. Don't use affix with the care, and don't mix tenses. So these are my instructions. And now with that, I'm going to close my today's recording. So here's a summary again. So next Monday, we're going to wrap up everything. If you want, I can give you a story about the career counseling. But if I'm not getting any emails from your end, then I'm just going to summarize everything. I'm going to give you questions that are needed in exam. Then we need to decide when is an exam day and time. Place will be modal. And that's about it. Nothing else that comes to my mind. Alright, let me think. Was there something else too? Well, I don't think so. So with that, you take care and see you on Monday. And now, if there's any practical matters or any communication, please send me an email. Alright, take care. Take care of yourself.